Hey, my name is Sionis Analakiso Koluntu. My matrix number is 241110999. Today I'm going to be talking about the Reynolds transport theorem, in short form RTT. The Reynolds transport theorem is a fundamental principle in fluid mechanics that connects the system approach, which focuses on a group of particles, to the control volume approach, which considers a fixed region in space. This theorem is essential for analyzing fluid flow in engineering applications such as turbines, pumps, and pipelines. I'm going to give you an easy example of what RTT actually means. So let's say we have a jar over here and the jar is filled with water. So what you're watching that's happening inside this jar is what we use the rule RTT for. So the rule RTT helps us to keep track of things like water, energy, or anything else that is moving inside and outside of the jar. So imagine of this jar. Imagine if we add more water inside of it, or if we shake the jar. So whatever happens at that moment, RTT is helping us to figure out how much is changing inside the jar. The second situation is where let's say we poke a hole in this jar and the water just keeps flowing out, or let's say we poke on top of it and water is flowing inside. So this RTT theorem helps us to keep track of how much water is coming inside of the jar and also flowing outside of the jar. So to simply state, the rule of RTT is that we get the change in the jar plus the flow of in and out equals to the total change. So that's what RTT actually means, and that's what the equation is, as we simply stated. Now, why do we use RTT? We use RTT because we need to know how much water is left in the jar, how fast the water is flowing in and out of the jar, and how much energy the water has while it is moving or flowing in and out of the jar. RTT not only works for water, it also works for every moving object such as air, cars moving on the road, and etc. Now, after explaining about what RTT is, let's get into the equation one by one. So first off, we have beta equals to P over M, where M equals to mass and P equals to the property of the system, such as mass, momentum, or energy. The rate of change of P for a system, which is written as dB system over dt, is related to two components in the control volume approach, which is of course the rate of change of B inside the control volume and the net flux of B across the control surface. This equation is written as dB system over dt equals to d over dt integration Cv rho beta dV plus integration Cs rho beta V times NdA, where the first term represents the accumulation of the property within the control volume and the second term represents the net flow across the boundary. Then we have the relative velocity. Velocity refers to how fast something is moving compared to another object. In fluid mechanics, when the control volume is moving or deforming, we measure the velocity of the fluid relative to the moving control volume. The velocity of the fluid relative to the control surface, V relative velocity, is given by V rel, which is V relative velocity equals to the velocity minus the velocity of the control volume. So by using this relative velocity in RTT, we can analyze systems where the control volume is stationary, such as a moving train or rotating turbine. Then next we go to RTT for non-fixed moving control volume. So if the control volume moves, the RTT equation adapts to include the movement of the control volume. Instead of assuming the control volume is stationary, we account for its velocity. So the RTT for moving control volume becomes dB system over dt equals d over dt integration Cv rho beta dV plus integration Cs rho beta relative velocity times NdA. So this version of RTT is crucial when analyzing systems like ships or rockets where the boundary itself is also moving. The next is alternate RTT for non-fixed moving control volume. So an alternate form of RTT is useful when simplifying equations for certain applications, and we can separate the total derivative of the system property B into components that include the movement of the control volume explicitly. The alternate RTT equation is written as dV system over dt equals to dO dt integration Cv rho beta dV plus integration Cv rho beta velocity v times n dA plus and additional terms for Cv movement if you have them. So this makes it easier to calculate changes when the control volume moves in a complex way, such as rotating or accelerating. Then we have the RTT for steady flow. So when a steady flow happens, the properties of the fluid like velocity, density or pressure, they do not change with time at any point in the control volume. This simplifies the RTT because the time-dependent term becomes 0. So the equation is written as 0 equals to integration Cs rho, which equals to density, beta v, which equals b, which equals to the velocity, times with n dA, and A is the cross sectional area. So in some cases with well-defined inlets and outlets, the flux term can be simplified to a total of outlets rho beta VA minus the total of inlets rho beta VA, where V is the velocity normal to the surface. RTT is applied to derive key principles like the conservation of mass and momentum. For instance, we can also say that B equals to M or beta equals to 1. The continuity equation of that becomes dO dt integration Cv rho dV plus integration Cs rho v times NdA, that is equals to 0. And with B equals to mv and beta equals to v, the momentum equation relates to external forces. So this theorem is very versatile and provides a bridge between theoretical analysis and practical application, particularly when simplifying assumptions like steady flow or uniform velocity profiles are made. So by understanding this theorem, RTT, Reynolds transport theorem, engineers can effectively analyze and solve complex fluid flow problems with ease. Thank you.